So let me. Okay, so as I was saying, there's no quiz tomorrow during recitation, and then you can check on Canvas your scores for the exam. I hope to post them by the end of the week, after all the makeups have taken place. Um, so I'll let you know once that's done, and I'll send you the solutions as well. Mm. Today, what we're going to do is just continue talking about convergence. Series. So if you remember last time, I was mentioning the ratio test. So what the ratio test said is that you have a series and you look at the successive ratios of like the terms in the series and look at how they behave. So what you would do is find the limit as n goes to infinity of an plus 1 in absolute value divided by an, right? So I told you that there are like three possibilities for what this could be. So if this limit is less than 1, then the series converges absolutely, which means that both with absolute values and without absolute values, it converges. So I'll write that just in explicitly. Okay. If the limit is more than 1, then it diverges. And I'm going to do an example about that in a moment after I'm done writing the ratio test. So if the limit is more than 1, both of these series diverge with or without absolute value. So, and the last option, which is the less interesting one for the ratio test because it doesn't tell you anything, is what if the limit is 1 or does not exist? So if it equals 1 or does not exist, then the test was inconclusive. So in that case, anything could happen. Both could diverge, both could converge, or only without absolute values converging. So anything could happen. Um, so last time I did an example for the first option, and for the last option, I'll do one for the case where the limit is more than 1. And then I'll give you at least a brief idea of why the ratio test works the way it's supposed to work without getting into too many details. But hopefully it will be plausible enough. Okay, so any questions about that, by the way, from last time? Does that make sense? So let's do an example of like option 2. So let's say you're trying to analyze the convergence or divergence of that series. And as before, I'm doing this one to just remind you what the factorial of a number is. Here, k factorial means k times k minus 1 times k minus 2 up to, so you multiply all the integers up to k. The first k integers are multiplied together. So, kind of like the interesting thing here is that like the factorial of a number is very large. It grows quickly. Like if you tried to play with it, like with a calculator, put 5 factorial, 6 factorial, 7 factorial, and you'll see those numbers like grow pretty fast. But at the same time, you have also been told like exponentials grow really fast as well, right? Like so 3 to the k is like an exponential, right? Like this. So if you also put like 3 squared, 3 cubed, 3 to the 4, 3 to the 5, that also grows quickly, you know. So it's kind of like a competition between two quantities which grow quickly, Um, and so like what the series what the ratio test will analyze is like, um, whether the numerator or the denominator like wins in the end in this case. Like okay, so according to the ratio test, what you here, the nth term is just minus 1 to the n and factorial over 3 to the n. And so what you have to consider according to the ratio test is you you put all of this in absolute values. So an plus 1 divided by an. Okay. Again, the effect of the absolute values is that it will get rid of like all the negative signs essentially. I'll kind of write it all the steps, but oops, I forgot let me, like, it's a fraction of a fraction, right? So, and all of that is divided by the m term. So, is that okay? I can sense. And now comes the simplification. So, when you have a fraction of a fraction, it is the numerator with the numerator of the first one with the denominator of the second one. So that will go to that will become the new numerator. So what do you get there? Like, let's forget about the negatives because they don't play any role. Okay. And then the other one, where you do the denominator of the first one with the numerator of the second one, and that gives you n factorial times 3 to the n plus 1. Yeah. Oh, why aren't we? You could have, sorry, you could have put right. Like, I guess you should have put everything in absolute value, right? It's just like those are kind of like, yes, like I should have put like everything with absolute value. It's just that since they're always positive, like right, like I could have like dropped them, but yeah, it's better to just put them everywhere. You're right. And okay, again, I'm kind of trying to write every single step. In practice, if someone wants to just like kind of go from there to here, like that's totally fine. I know what's going on, but I'm trying to kind of like show you a bit more steps in between. And then what you can do is that you know, there's like this formula for the factorial of a number. which is that the factorial of a number is that number times the previous factorial, which makes sense if, if you think about it just like with some numerical examples. And then 3 to the n plus 1, you can also break it as 3 to the n times 3, just to get some simplifications. So that allows you, that will cancel out the factorials. And this will also cancel out the 3 to the n's. So like the ratio, so just to summarize, what we just found is that the ratio of the terms is what? Is n plus 1 over 3? That makes sense. Yes, fine. And so in the ratio test, you take the limit as that goes to infinity. But before taking the limit, like, what that means is that the ratio, like the ratios are getting larger and larger, right? Because you're getting n plus 1 in the top. So what that means is that when you look at successive ratios, these numbers keep growing. And so, like the terms that you're adding in a sense are always like keep increasing. So since the limit as n goes to infinity of n plus 1 over 3 is infinity, which is greater than 1, which is greater than 1. The ratio test says that the both diverge with or without absolute value. That both yeah. If I can explain how that happens again, or what you should put it, can you explain that? Oh yeah, yeah, sure, sure, sure. Is that yes, right. It's easier to kind of like, let me just draw a few test cases so that you can see it more clearly. Um, so what happens is like if you kept going doing this, right? Like what is n factorial? It's 1 times 2 times 3 times 4, dot 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 dot, up to like n. And what is n plus 1 factorial? It is 1 times 2 times 3. Oops, let me just continue here. Up to n, but now you have to do like an extra one, right? Is that making sense? And if you see like the first n factors correspond to like n factorial. So this is precisely like n factorial. So that is where like it comes from. Which is sometimes called like the recursive definition of the factorial, because if you remember when we talked about sequences, you could think that there's like a sequence which is like the sequence of factorials, right? And so what this is telling you is how to find the nth plus 1 term in terms of like the previous step, right? So it's just the fact, like it's n plus 1 times like the previous factorial. Um, But yeah, this is like an insane, I mean, the factorial is very important in combinatorics or probability theory if you ever have to take that, because like that is involved, that is related to in how many ways you can distribute like a number of objects, like permutations of like I said, like the typical example is like if you had like n balls and like n locations, and how many ways can you arrange the n balls among those n locations, and that like, you know, if you're not allowing for repetitions or anything like that, like the number of ways is like n factorial or things like that. So um like they become insanely huge numbers like pretty fast, like okay. Any other questions about this? So roughly like between this example and the previous and the other two examples from last time, that gives you like an example for each of the cases in the ratio test. Now what I'll just give you is like a brief like idea of why it works the way that it's supposed to, without getting too bogged down into the details, but it's still useful to like understand what's going on. So, oops, sorry about that. You know, okay. So why is the ratio test the ratio test work? So I'll kind of like explain the first possibility, which is like the most interesting one. So let's talk about case one where the limit, right, of these ratios is less than one, right? So if the limit is less than one, um, here's like a way to represent that visually. So let's imagine that you draw the number line. Here you have the number one, right? Uh, here, let's put the limit in blue. Here you have the value of the limit, right? And if the limit of the ratios is L, what that means is that eventually, what does it mean for a limit to exist? It means that eventually you are pretty close to the limit, right? That's how you should think about a limit. That as you increase the value for n, you get closer and closer to the limit. So eventually, like all the ratios are going to be kind of like in a around L. So like just imagine that there's kind of like an interval around L. Um, I don't have to be super precise, but like this interval is like small enough, so you can think about it as like if you have seen like this delta notation, you can think about this as being like L plus delta L and L minus delta L, where like delta L, whenever you write delta in math or physics, you want to think about that as being small enough. So there's kind of like a safe zone around the limit, and like eventually all the ratios have to be dropped into here, right? Oops. So eventually can be found inside this interval. Is that okay, everyone, with me? So far, so good, making sense? Um, so again, to kind of give you like a sense of what's happening, let's say that that occurs after the 100 ratio, okay? So suppose that happens starting with what? A of 101 divided by A of 100. So what that means is that, uh, let me just kind of like draw the interval again here. So what that means is that you have the limit here, you have L minus delta L, you have here L plus delta L, right? This is kind of like our safe zone, and somewhere on this interval is somewhere on this interval would be A of 101 divided by A of 100, but then the next ratio would also be there. So here, maybe somewhere in here is like A of 102 divided by A of 101. And then maybe here is A of 103 divided by A of 102, etc. And all the other ratios like kind of live in somewhere in there. Okay? Yeah. Oh, so here the only thing that I need uh, for the extent is that it doesn't touch one. And you'll see why I need that. After that, you know, anyone would have worked, but I don't want my ratio to kind of include one because I will compare this to a geometric series in a moment, and it will be important that, you know, a geometric series converges when the R of the geometric series was less than one. So that's why I want to kind of like stay away from one. But except for that, like, like of course, like once you give numbers to this, like if the ratio had been like, if that limit had been 0.5, then this would have been up to 0.9 or like 0.999. Like it just really has to be a little bit before one and then uh, okay, now, but what does it mean? And in fact, like just to kind of leave put this comparison with the geometric series more clear, I'll call this number R, okay? Just to kind of like put things like get it ready to do what I want to say. Okay, so let's call this R. So what does it mean for all these numbers or all these ratios to be inside this interval? That means that every one of these ratios has to be less than R, right? So each of like these ratios must be less than R. So what does that mean? That means that A of 101 divided by A of 100 has to be less than R. It also means that A of 102 divided by A of 101 is less than R. It also means that it also means that A of 103 divided by A of 102 is less than R, etc., etc., etc. All the successive ratios, you know, A of 1,000 divided by A of 999 is less than R. Any ratio, A of a trillion divided a trillion and one divided by a trillion, A of a trillion is less than R, etc. Okay? Yes.
Is say that it's just any ratio value less than one, but R is less than one, so doesn't every value between R and one also one?
Right, you could yes, like as long you could have replaced this right yeah, like if R had been like 0.9, it would also be that all of these ratios are less than 0.999, right? That's all good. I mean, there's nothing wrong with that. All that I'm saying is that I chose kind of like the only thing that I'm saying is that because the limit is less than one, right? Uh, you know, this can be a bit confusing, but where am I? Yeah, all that I'm saying is that because the limit is less than one, there is some space in between those two numbers, right? So you create kind of like a safe zone between them. And no, it doesn't matter how big that safe zone is, right? But I'm just calling where this safe zone terminates R. But yeah, the ratios are big are less than R, but they are also less than another number greater than R, if that makes sense. I just need them to be less than R.
So essentially just for saying,
You could have been like you could just have been any interval provided it was really leaving some space with one because it will be clear like in 2 seconds because you'll see like an powers of R in a moment, and since R is less than one, there will be a geometric series that converges. So I'm trying to kind of like do a comparison test actually. That's where I'm headed. But yeah, like it's kind of like a safe zone kind of thing. But right, but like now I'll show you how this is supposed to go. Like so, for example, what does the first inequality say? Like it says that A of 101, right? If you multiply both sides by the denominator, that tells you that it's less than R than A of 100 times R, right? What does the second inequality says? What about the second inequality? It would say that A of 102 is less than A of 101 times R, right? So far, so good. But I know that A of 101 is also less than A of 100 times R. So I kind of will insert this other inequality into here. And I now get an R squared, right? Let's do the third one because hopefully you see where I'm headed now. What is the third inequality telling me? It says that A of 103 is less than A of 102 times R, right? But what is A of 102 less than, according to this thing, like you kind of put it into here. And this is what? Less than A of 100 times R cubed, right? And if you were to keep going, right, like like for example, what would the 10th inequality say? It would say that A of 110, right, is less than what? A of 100 times R to the 10, right? And so, what I'm kind of trying to show you is that, um, all the terms are being bounded by a geometric quantity, right? Like they're just being bounded by R to something. So if you were to kind of like do like that, so the idea, and again, I don't want to focus too much on the proof, but I did want to give you like a sense of how it works. But so the idea is that the series, right, like of the terms, right, is really controlled by, in this case, like, like A of 100 times R to the K, you know, this is just a constant, it doesn't really matter. But this is then like a geometric series with R less than one, which converges because of how we know like the geometric series behave. So which is geometric and geometric with R less than one, so converges. I think making sense kind of like reasonable. Yeah. Oh, this tense inequality. Oh, oh, this one. Like, what is this series? It's kind of like, I mean, if you wanted to be a bit more precise, what does this mean? Like you could like make, that means to add up the terms up to 100, right? For example, plus the terms from like, you know, what, like from 101 to infinity, right? All of these, well, I guess like I should have subtracted like 100 from here, like, then it doesn't, um, you know, like what I'm saying is that each of these terms starting at 101 is smaller than A of 100 times some power of R. So these are just like finally made. You don't care like what this number was. And all of these here, like each of these pieces is individually controlled by something that looks like this, like A of 100 times the power of R. So that is essentially like, like basically geometric series. I mean, you could be a bit more careful to put the indices correctly and all that stuff, but kind of like the idea is that like once you start at 101, like all the terms are bounded by powers of R. And that's enough to kind of like, say that the series has to converge because R is less than one. Is that making sense? Yeah. So kind of like this is the philosophy with the series is that convergence only cares about what happens at the very end. You could have like the sum of the first 10 trillion terms that doesn't affect the convergence or divergence of the series because a trillion, 10 trillion is small because you're going to infinity, right? Everything is small compared to infinity. So yeah, like it does, like, when you control like a series, it only matters to control what you call like the tail, like what happens at the very end of the series. So at the very end of the series, all the terms are being controlled by like the successive powers of like this number R, and that's all like that you care. But again, like it's like I just wanted to it's a good example to go through. Like not that I want to go through many proofs in the course or anything like that, but what's nice about this is that it shows you why the geometric series is so useful, because it is a useful series to have that can be used to control other series. So in this case, like it can be used to control like this other one with the ratio test, you see. But right, in practice, you can totally ignore this and just like say, okay, the ratio test says whatever it is, it's a black box. But like kind of like the idea behind it is kind of like this like comparison with the geometric series. Okay, so there are only two tests left to discuss about convergence and divergence. I think what I can, yeah, like the next one is the root test, which is very close in spirit to the one that we just did. So it's useful to kind of like mention it right now. So the next test is called the root test. And here again, you want to study the convergence or divergence, or like you want to determine the whether the series converges or not. But now in the root test, what you consider is the nth root of the nth term. So here you consider the limit as n goes to infinity of the nth root of the nth term in absolute value, because like the terms could be positive or negative, so you want them to for the root to always make sense. And kind of like the nice thing about this limit is that it has exactly the same behavior as the ratio test. So if it's less than one, there's convergence for both series with or without absolute value. If it's greater than one, there's no convergence for neither. And if it's one or does not exist, we're inconclusive. So let me write the three cases here. So the nice thing is that you don't really have to remember that much else because it has like the same behavior. So if this is less than one, both converge. Okay. If the limit is more than one, then both diverge. And if the limit is one or does not exist, so if it's one or does not exist, then the test is inconclusive just as before. Yeah, right. So yes, if you I mean, kind of like a good rule of thumb sometimes at the beginning is that yeah, you can check, oh, would the ratio or the root test work? And if you happen to be stuck with one or does not exist, then yeah, you then have to look, oh, maybe like a comparison, like maybe one of the other tests works. Like there will be always like, like a test that would work, but yeah, like that's, I will kind of give you like a chart, I guess, with all the tests. But like, yeah, like eventually, you would need to go through one of the others. But you again, like you kind of develop a set. Sometimes like the problem is say explicitly use the ratio, the root test or whatever to study the convergence or divergence. But if it doesn't say anything, then yeah, you're kind of like, we'll have to do some trial and error to see like, what could happen. The nice thing about these tests is that sometimes like, again, like you could try to find them using like an integral test or other things, but sometimes like finding these limits are faster than the comparisons with the integral. So like there's a lot of redundancy for this type of problems because many times more than one thing works. You know, it's just that like some become faster than than the others. But so let me give you like an example, and the proof, like not that I will go into it, but the proof is more or less exactly the same idea that I just mentioned. There is a comparison with a geometric series. It's almost word by word what I did before. So it's like a very similar concept. But let me just do like a quick example because like it kind of like is analyzed in a similar way. So so this is a case where like say the ratio test would have worked, say for example, but like also the root test would work. So you called an the nth term, um, and then you've considered the limit as n goes to infinity of the nth root of the absolute value of a sub n. And again, once you take absolute values, you can forget the negative one to the n, so you just get this. Is that okay? Is that making sense so far so good? So here, like if you want to find this limit, one way to write it, which is a little bit more convenient, it's like to take the square out. Because the n, like the limit as n goes to infinity of the nth root of n is kind of like a classic L'Hopital type limit. So if you kind of happen to remember that this one is one, then you're good to go. You can just say that that's one. If not, like we can do like a quick L'Hopital reminder of how that works. So uh, called let's call this like usually it's easier to take the logarithm first. So call like x sub n like root of n to of n. So the natural log of x sub n is the log of the nth root of n, which is 1 over n, the log of n. Okay. And it's easier to just take like the limit of this than, There's also the other way where you can write it as e to the ln first. So that means that the limit as n goes to infinity of the natural log of x of n by L'Hopital is the limit as, well, I mean, the limit as n equals to infinity of natural log of n over n, and this by L'Hopital is the limit as n goes to infinity of 1 over n over 1, and that's just, that's 0. And then the limit of as n goes to infinity of x to the n is the same as the limit as n goes to infinity of e to the ln of x to the n, but we already know that this is e to the 0 because of what we just did, so that's just 1. Yeah. Yes. Uh, you mean like the thing that I wrote in this part? Sure. Is that making sense? So again, like you can totally use that this has to be 1. That's fine. Like, but if you forget about it, like you just take ln on both sides, and it's not such a bad calculation. But so this would give 1/3. And because that's less than 1, the root test says that it converges. Okay. So let me put this as an aside. Let's move it here. So this is like an aside. So less less than 1. So there's absolute convergence because of the root test. Got questions about this? Yeah. Yes. Oh, the things that you're taking absolute values in the root test. Yeah, yeah. So like usually that's the thing with the ratio and the root test. You always get rid of all the negative stuff. Yeah, yeah, yeah. Which is why it is useful to talk about the absolute convergence, because absolute convergence had to do with the absolute value of the series. And that's why, like, kind of how it works. No, but that's any other one? Okay, so in the remaining minutes, at least I'll kind of briefly introduce like the last test, and I'll talk more about it next time. But which is this is also like a useful one. And this one is kind of like really complementary to the other, so it does help in many situations where this fail. So it's called the alternating test, or like, well, like an alternating series. So I'll just put as a remark that this one is complementary to the previous ones, especially when you get 1 as a limit for the root or ratio test. So this one complements the root and ratio test in many circumstances. So first, before giving you like a definition, kind of like the example of like alternating series to keep in mind. Um, is something like this. -1 to the n over n. So that, let's say -1 to the n plus 1, so that I start with something positive. So this is would be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 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 plus. Another one would be like, here's another one, would be something like, okay, so let me try to work some examples here. So now it starts with negative because it's -1 to the n now. So it would be what? It would be -1/2, then plus 2 squared plus 1, that's 4 plus 1, that's 5. Then minus 3, and then 3 squared is 9, plus 1 is 10, and then plus 4 over 4 squared plus 1, that's 16 plus 1, so that's 17. Oh, let me do another one. Minus 5, 5 squared plus 1, that's 25 plus 1, 26. Okay. Okay, so what do these two have in common? Well, first, they're called alternating because if you look at the coefficient, like the summands, they alternate between positive and negative. It doesn't matter if it starts positive or if it starts negative. It's just like positive, negative, positive, negative, positive, negative, like in either order, right? Like it just switches sign from one term to the next. So let me just like explain that part first. So they're alternating, and this just means that the terms like the summands change sign from one to the next. So it can start again, like the series could start being positive or could start being negative. It doesn't matter, like Yes, sorry.
Maybe if it's like, if you have like two terms that are positive answers.
Yes, I mean not by the strict definition, but that's kind of like the philosophy with the series, right? If you even if you had like the first 100 terms all positive, but after that it alternates, if you want to analyze the convergence or divergence, it doesn't matter what the series wanted to do at the beginning, right? So you kind of like forget about the 100 term initial for 100 terms, and you kind of realize, okay, after that it starts alternating, right? So in reality, the only thing that you care is that the series eventually is alternating, and by eventually that it becomes alternating after like a finite number, right? Like after, so yeah, like the first 1 million terms could be all positive or all negative, but if after that it starts alternating and satisfies something else that I still have to write, which I haven't finished, then like you could apply this same test. But in practice, most of for like what we're doing, yeah, like the sequences would start like being alternating from the beginning, but there's, like the convergence or divergence again of a series only cares about what happened at the very end. So the series can be completely crazy, no pattern whatsoever at the beginning, and it wouldn't affect it provided it continues to be alternating. That makes sense. But yeah, not by the strict definition, but like you could still like use the test. So right. So what we want for the test that I'm about to write is that you want the terms to be alternating, and you want that the terms to decrease in absolute value and go to zero. Okay. So the extra condition that we're going to want for the alternating test is that we have an alternating series with the property the sequence of absolute values, the sequence is decreasing and their limit is zero. So in other words, in absolute value, the summands are decreasing, like the summands are decreasing in absolute value and converging to zero. Okay. Which if you so actually let me do like a picture here of how what you should think about. So maybe this is the first term, then this is the second term, then this is the third term. Okay, I'm trying to make them so that one is like smaller than the other. It's kind of clear that they kind of become smaller successively. I think this is kind of plausible that they are shrinking, right? Right, so like imagine like the height being the value of the number, right? So if it started positive, it switches to negative, it switches to positive, negative, positive, negative. But the height of the building, like in absolute value starts it shrinks, right? So this one in height, if you put the absolute values everywhere, this one is taller than this one, which 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 is taller than this one, in absolute value, right? Like the actual height of like these numbers. Yeah. The summons. Yeah, yeah. Let me, yeah, like, oops. Let's put the S. Oh, like the summons, like, the things that you're summing, like, like each of the ANs, like, if you do if you say 1 + 2 plus 3 plus 4, like one of each of these numbers is called like a summand, like the things that appear under the sum, like yeah. But if not, I just meant this. The picture is kind of maybe more clear. I just mean like the terms like flip in sign and they shrink in absolute value, like which as no, but the thing is like I'm not requiring the sum to go to zero. I'm just requiring the individual terms to go to zero. Right. Like because yes, in absolute value, if you were adding them, that like actually, like that could potentially continue increasing. But it's more like that the heights like the individual heights in this picture are going to zero, not their sum necessarily. Yeah. Correct, yes. Anyone else? And I mean, I'm almost going to wrap this out because like I have bombarded you today with tests. But what the alternating series test says is that under these conditions, like the series converges, like the ordinary series, like you don't know whether with absolute value it converges or not, just like the regular series. Like so, under these conditions. And the series with absolute values may or may not converge. Okay. So for example, I'll mention this like next time, but like the one with -1 n over n that will converge because of like this alternating series test. But if you put absolute values, that's like the harmonic one, like 1 over n, which diverges. So like if in absolute values, you do have to kind of like analyze the series differently to see whether it converges or not. Um, yes. Or you want to answer?
Okay, so just to make sure I understand it, previously, if the function or like the A of n terms were decreasing, that's not enough to say that it's convergent, right?
Correct, yeah.
For example, like 1/x.
Yeah,
Right.
right, like having decreasing does, like, but the alternating helps, yeah,
Right.
that's what
So-
makes it.
If it's decreasing and it's alternating, it's convergent.
Yes, correct. Yes, decreasing to zero, right, with as long as the understanding that it's going to zero, because that is needed by the nth term test, right, like you always have to go to zero for the series to converge. Maybe just to kind of finish for today, like I'll show you like this quick animation because it's very cute, but and I'll explain what's happening there next time. Yes. Oh no, I'll explain it next time. Yeah. But I said I don't have enough time and I like, I feel like that's too much for today. But I will kind of show you like a cute picture of like, what's going on here. So this is kind of like the alternating series, like like -1 to the n plus 1 over n. For some weird reason, the person decided to call this x, but just think of n, like it is the same. So the first term, the first partial sum is just 1, right? Like it's just the first term, which is here, right? Then the second term is 1 minus 1/2. That's why you get 0.5. So this is like the first sum, like the first partial sum, the second partial sum. And then the third partial sum lands here. Then the fourth partial sum lands here. The fifth, okay, you'll see you see there's some alternation between the partial sums, which is very fun. And then it's kind of like all like getting closer and closer to something, and that would be like the limit of the partial sum, the series. Of course, I'll explain a little bit of why it happens with that pattern. But the thing is like because it changes in sign, like that's why the odd ones end up being all on one side of the line, and all the even partial sums on the other side, and that's kind of like they both are like nesting like towards like a point in the middle, which is the middle. But again, I'll kind of give you like an idea of why that works, but it feels, of course, in practice, you just use it, but it is like a very useful test because it does cover other situations. So let's end here, and then I'll tell you a bit that next time more about the alternating series.